Everything ends. Not just you, not just the sun, but the stars, the galaxies, and very likely the universe itself. The strange part isn't that it ends. It's that for decades we thought we knew roughly how, a slow, quiet fade into cold and dark. And then, in the last 2 years, fresh data did something cosmology almost never does. It reopened the question. So let me walk you through the real ways the universe could end, which one the evidence actually favors, and why scientists are suddenly less certain than they were just 5 years ago. Start with the one thing that decides all of it, the expansion of space. Ever since the Big Bang, space itself has been stretching, carrying the galaxies apart from one another. For most of the 20th century, the great open question was whether gravity would eventually win, dragging everything back together, or whether the expansion would simply coast onward forever. Then, in 1998, two teams of astronomers measuring distant exploding stars got a result so strange they assumed they'd made a mistake. The expansion isn't just continuing. It's speeding up. Something is pushing the universe apart harder and harder as time goes on. We still don't know what it is, so we gave it a placeholder name, dark energy. It appears to make up roughly 70% of everything that exists, and yet we cannot say what it actually is. And here is the crucial part. The entire fate of the cosmos comes down to a single question about that mysterious stuff. Does it stay constant, grow stronger, or fade away? Each answer is a completely different ending. Take the answer most cosmologists would have given you a few years ago, and still the leading one today: the Big Freeze, also called heat death. If dark energy stays roughly constant, expansion keeps accelerating, galaxies keep flying apart, and the universe simply winds down like a clock that no one rewinds. It happens in stages. Right now we live in what astronomers call the stelliferous era, the age of stars. But stars need gas to form, and that supply is finite. In roughly 100 trillion years, the last star will burn out, and no new ones will ever be born. Before that, something quietly sad happens to the night sky. As space expands, the distant galaxies are carried beyond our reach, their light stretched until it fades from view. Astronomers far in the future would look up and see only an empty black sky, with no way of ever knowing the wider universe had been there at all. Then comes the degenerate era, lit only by the cooling embers of dead stars. After that, the objects with any real mass left are black holes, the black hole era, where these giants slowly devour what remains. And even they don't last forever. Through a subtle process predicted by Stephen Hawking, black holes very gradually leak their energy away and evaporate, the largest of them taking something like 10 to the power of 100 years, a one followed by 100 zeros. When the final black hole is gone, you reach the dark era, a cold, black, all but empty space where nothing ever happens again. No explosion, no bang. The universe just runs out of usable energy and stops. But that gentle ending depends entirely on dark energy behaving itself. Suppose instead it grows stronger over time. Physicists call that phantom dark energy, and it leads to a far more violent finale, the Big Rip. Here the acceleration doesn't merely push galaxies apart, it intensifies without limit, until it overpowers every force that holds anything together. First, the galaxies are torn away from each other. Then individual galaxies are shredded, the stars scattered. Then solar systems are flung apart, then planets stripped from their suns, and in the final fraction of a second, even atoms are pulled to pieces. The universe doesn't fade. It's torn open. And unlike the slow freeze, this one has a sooner deadline. Depending on exactly how dark energy behaves, the earliest a big rip could occur is around 22 billion years from now. On a cosmic scale, that's almost around the corner. Now the third classic possibility, the mirror image of the Big Rip, the Big Crunch. If dark energy were to weaken or reverse, gravity could eventually regain the upper hand. Expansion would slow, halt, and then run backwards. Galaxies would fall toward one another, the universe would heat up as it contracted, and everything would end where it began, crushed into a single, unimaginably hot, dense point. Some versions of this even imagine a bounce, a fresh Big Bang on the far side, the cosmos starting over. For years, this scenario was treated as all but dead, because the expansion is so clearly speeding up, not slowing down. But hold that thought, because it has just come back to life. Here is the discovery that reopened everything. A project called DESI, the Dark Energy Spectroscopic Instrument, has been building the largest three-dimensional map of the universe ever made, using 5,000 robotic fibers to capture the light of millions of galaxies and trace how they've spread apart over the last 11 billion years. And in its 2024 and 2025 results, it found something nobody expected. Dark energy may not be constant after all. The data hint that it was stronger in the distant past and has been gradually weakening, becoming, in effect, less pushy over time. Now this is still a hint and not a verdict. It isn't yet certain enough to call a discovery, and extraordinary claims demand more evidence, which other surveys are racing to gather. But if it holds up, it rewrites the ending. A weakening dark energy makes the violent Big Rip less likely, and it quietly puts a slowing expansion, even an eventual crunch, back on the table. The single number that governs the fate of everything is one we have only just discovered might be changing. And there is one more possibility, a wild card that waits for none of this. It comes from the Higgs field, the thing that gives particles their mass. When physicists finally measured the mass of the Higgs boson, the numbers landed in an oddly precarious place, not clearly stable and not clearly unstable, but what they call metastable. Picture a ball resting in a shallow dip partway down a hillside. It looks settled, but it isn't truly at the bottom. If the vacuum of our universe is like that ball, then somewhere, someday, a microscopic bubble of true vacuum could form and expand outward at the speed of light, rewriting the laws of physics inside it and erasing everything it touches with no warning, because nothing can outrun light to tell you it's coming. The reassuring part, if you can call it that, is that the predicted wait is vastly longer than the entire current age of the universe, so it is genuinely nothing to lose sleep over. But it's a humbling reminder that reality itself may be only provisionally stable. So where does all of that leave us? The honest answer is that the slow freeze is still the frontrunner. If dark energy is constant, the universe ends not with a bang, but with a long, cold silence, the stars gone, the black holes evaporated, everything spread too thin and too cold for anything to ever happen again. But the most important thing to say about the end of the universe right now isn't the answer. It's that we are suddenly less sure of it than we were. The fate of literally everything rides on what dark energy is doing, and the newest and best data we have just told us it might not be the simple, unchanging thing we assumed. We aren't reading the last page of a finished story. We are watching it be written, and the ending is still very much in play.